We're very happy. You should.
Should I say got it?
Yeah. Oh, I think I got it here.
Okay.
It's good. All right. We're very happy today to have LianTao Wang from University of Chicago. He's going to tell us about some cool gravitational wave physics, especially from inflation. So go right ahead.
Okay. Thanks for the invitation. Nice to visit here. And okay. So I think I was at NYU more than 20 years ago. Briefly, it was a graduate student, the mayor of a block from here. It's still there. It's still called the physics field.
And then we kicked you out, right?
And yes, I flunked out and get to another school. Yes. Okay. So I'm going to talk about gravitational waves. Just sorry. Oh, okay. Just a little bit of a motivation. So early universe. I think thinking about early universe, this is the picture that most of us have. There is so this is the simple picture of cone moving horizon, and we think there is inflation and there's reheating and some radiation and domination going to matter and so on. Okay, so that's the usual picture. And but then you can ask, what do we learn? What do we know? Really know about this picture? I think this is what we really know. What we know is that there's some large scale. At a large scale, the mode presumably coming from some earlier stage of inflation. This is supported by CMB and the large scale structure measurements. And we also know a lot about what's happening after the event. This doesn't mean that you can't put in new things in it, but still, at least we know those things. We have a lot of experimental observational evidence for what's happening during those periods. This obviously leaves the question that we didn't quite know about either what happened during inflation after the CMB mode exit horizon, and we also don't quite know what happened after reheating. So going on. Okay, and now the lot of the reason that we didn't know about this stuff is that there's this thing called the thermal equilibrium in early universe that tends to wipe out a lot of the information, and this tells for this reason, I think the gravitational wave signals are particularly interesting because they are not susceptible to this memory loss. Okay, and from the earlier. And this is, there are lots of works on post-inflationary sources of gravitational waves. And this is just one of those. I mean, there are many this kind of plots. This is just one of those. And people thought about many different sources that can give you generate gravitational wave signals post-inflation. For example, I think this is a cosmic string. This is some phase transition and so on. But typically, what's needed is something quite dramatic needs to happen because generating gravitational waves is not easy. So you need some pretty violent process to generate them.
What's the dashed blue curve on the left with the shading?
You mean this one?
Yeah.
I think this is the R value measurement. I could be wrong. I didn't look into this very detailed. And I think this is the inflationary prediction. Okay, now then the question is, what about this period? So what about what can gravitational wave? What kind of sources that can generate gravitational wave from this period, and what kind of information can tell us about the dynamics during this period? So just to set the perspectives, so I think here is depends on when do you think the gravitational wave is generated, and they're usually generated with a frequency. Typical frequency is the size of the horizon around that time, and then they just redshift. So for example, if gravitational wave is generated roughly 40 e-fold till the end of the inflation, I'm still assuming some standard 60-ish e-fold inflation. If something is generated, for example, 40 e-fold before the end of inflation, then you redshift it, it's roughly translating into nanohertz around the, it's in this in the range of pulsar timing arrays and so on. And but if it happens a little later, let's say 20 to 30 e-fold, and then it's roughly in the range of Lisa, and if it's even later, closer to the end of inflation, it could even get into the frequency band of LIGO and also Einstein telescope, cosmic explorer, and so on. So this is just to say that we do have a range of observations. In principle, they can be sensitive to the signal that's generated during the later stage of inflation.
So this is all independent of the scale.
This is independent of the scale of the inflation, and this a little bit depends on when the inflation will end, or whether there will be a matter domination and so on. This a little bit depends on for drawing this picture. I'm assuming the simple picture where just instantaneous reheating. Yeah. I mean, it's also very rough. I'm giving any order. So. Okay, now the question is what kind of sources that can give you, as we said, usually you need something rather dramatic to happen to generate some interesting signal. So what kind of sources that you can imagine that give you the gravitational wave, and what are the shapes of signal? It means that if we see some gravitational wave, can you actually say tell it's coming from this era, or what the what physics you can learn from the shape of the signal. Okay, so the rest of this talk, so I don't have a universal answer to these questions. It's still a lot of things are still ongoing, and I'm going to cover some of the recent development, focus on my own work, obviously, but also mention a few others interesting examples. It's more like a little bit of overview with some details on the work I've done. Okay, and so let's say I wanted to talk about several aspects of it. The first class is what I will call primary gravitational wave. You will see what I mean, but let me just first explain that people. So primary means that you literally have some source, relatively localized in time during inflation, and they generate the gravitational wave, and the gravitation will propagate to us. Okay, this is what I mean by primary. So there's some T mu nu that source in gravitational wave during the inflation, but the first reaction you may be saying that is that okay, this is not observable because the inflation is going to dilute them, because radiation dilutes by form of radiation. I think this is this little argument is supposed to show you that it's not quite the case. Okay, so it depends on the frequency of the gravitational wave mode you are considering. Okay, so let's say if you are considering a mode with a frequency k, and it will start to evolve going outside the horizon during this little period evolution. It does dilute like 1/8 volts. So that's giving you this factor. And then once it's outside the horizon, it doesn't dilute as a 1/8 to the fourth anymore. It dilutes like 1/8 squared. Okay, the energy density in the gravitational wave, and it just go over there, and it's just a little simple algebra to show that this amount of dilution from the gravitational wave outside the horizon to its re-enter, this amount of dilution is the same as the radiation dilution from here to here. Okay, from the end of inflation to the same point. It's just a simple exercise to show, and therefore, so Therefore, so this part is the same as if you want as the radiation. The only additional factor is a little bit of dilution here. And let me just again I copied that formula again. So yeah, the later part is just the same as radiation. A gravitational wave is often being compared, in the unit of omega radiation. Omega radiation is 10 to the minus 5. But the typical sensitivity of the things that we're talking about happening in the future is 10 to the minus 14-ish. Okay, so this is there's still some ways to go. Okay, we can see signals much weaker than just radiation. And also I want to say that typically you'll see that the peak the peak spectrum of gravitational wave being generated is exactly when the k is the same as the horizon size. So for those signals, they don't really suffer any dilution. They just dilute the same way as radiation. Anyway, so this is showing you that it's for gravitational wave generated during the inflation. You don't really need to worry about paying that penalty. Okay, of course, this is a k-dependent thing.
The A star, is that normalized just A is 1 today or?
Yeah.
Okay.
So now what are the sources? Okay, the basic source is that inflation produce particles. So they also produce gravitons. So that's for the inflationary tensor, right? So this is but this is very, very small. Okay, we need something much more dramatic than that to produce a observable signal. Well, unless the inflation scale is very high, then in that case we'll see them in our measurement of the future generation, maybe S4 and so on.
So the light blue line is what inflationary model?
I think it's just the inflation model with only sensitive to the scale, right? So that's the R basically.
That's at the upper bound.
Yeah, I guess I didn't look at that. It's in that reference. I didn't look at. I just took the picture of the
I think it has some tilt.
It does.
Yeah, the tensor spectrum.
Okay, so
Proportional
assuming that
to epsilon.
I see.
And if you want to be sensitive by Planck, then epsilon is larger. Like,
yeah.
So then I guess that tilt shows up. Something like that.
You mean this part?
Yeah.
Yeah, absolutely. Yeah, I'm just saying that in this piece is for the later, for these probes, right, in order to be visible, you need to.
Yeah.
Okay. All right. So what kind of processes can generate the gravitational wave around that time? Primary sources, for example. So one of the things you can think about is that just the evolution of the inflaton itself can trigger something else. If inflaton couples to something. And this because the simple fact, also well-known fact that is that the inflaton tends to traverse a large distance in field space. This is the simple formula. Like even if you think that just during a few e-fold, if epsilon is not tiny, very small, we talk about the still semi-high scale inflation, then this is really a big distance in field space to travel. Even if you are still, technically within, try to maintain yourself within the effective trajectory.
What's the typical size of epsilon?
What's the typical size? I think the highest, the highest scale for higher scales, epsilon is around the 10 to the minus 2, between 10 to the minus 2 and 10 to the minus 1. But if you lower the inflation scale, the epsilon can be much smaller. Okay, so yeah, so usually we think inflaton has some approximate shift symmetry because the flatness of the potential. But on the other hand, we also do expect that the shift symmetry to be broken by some higher dimensional operators, which can couple inflaton with some spectator sector. If I have some operators like this, I imagine this inflaton to travel a large distance, in the field space, this can generate something quite different, quite dramatic in the spectator sector. Okay. So that could be the source of gravitational wave. Yeah, so this is just a simple toy model that you can simply write down a inflaton coupling with the spectator sector with spectator sigma, and this effectively corrects the effective mass of the spectator. Okay, so that's just one simple example, and you can even change the sign of the mass term, for example, and this will easily trigger a first order phase transition. And the first order phase transition will generate bubbles and so on that generates gravitation. Okay. Let me just spend a few more words on what kind of phase transition we're looking at. So there's some analysis about what kind of phase transition we are looking at. You're looking at first of all, you look at whether this phase transition finishes. Basically, whether they can the bubble is nucleated enough and they occupy the whole space. Basically, whether they percolate. So they generate gravitational wave when they percolate, because the bubble wall starts to collide and so they generate also gravitation. And we also want this to be a first order phase transition, so that I'm not showing you too much detail here, but roughly speaking, you need this kind of a hierarchy. So you need this kind of hierarchy, and which is this just means that the beta is the typical inverse size of the bubble, and this is roughly the scale of the spectator sector. I use the mass of that spectral field as a representative. And I also want this to still to be a spectator sector, so that it's not dominating over the energy density of the inflation itself. Okay, so this is a kind of hierarchy that I'm working with. So in this case, you see that the size of the size of the bubble tends to be much smaller than the size of H. Okay, so in the model that we are considering, so in those cases, also the typical collision time of the bubble is also, you can be estimated by the size of the bubble, basically. Okay, and this means that I almost have an instantaneous source of gravitational wave. Just the bubble collision finish during a time that is much shorter than the Hubble time. Okay, so this is the.
Sorry, I missed this, but like sigma's getting a bev essentially, right? So
Sigma is getting a bev.
and so it changes the inflaton mass. How much does that change?
Yeah, so I'm assuming that the back reaction on the inflaton is very small. That is what I'm assuming. I'm assuming this C is very small. Okay, so it's a so inflaton has a bev on the order of big M. So the movement of inflaton has a bigger, very big impact on the sigma, but not the other way around. Okay. That's what I'm saying. The inflaton has to move some big field distance. Sigma doesn't. That's the.
Is there a worry during like inflation, like you nucleate these bubbles, they expand at the speed of light, but then space itself is expanding so rapidly that they never actually meet? I mean,
yeah. So this is called the percolation property, right? So exactly this is a, you can this is the standard I think Eric Weinberg boost analysis. You can go through that. You see that this is the kind of hierarchy you want for percolation to happen. So this is just saying that in our model, if you plug into some numerical code, and you do get this kind of a hierarchy. So the beta is much bigger than H. Okay, so let's. I'm going to talk about. Given that, I'm going to talk a little bit more about the shape of gravitational wave. signal do you expect. So to do that, it's important to look at the 3 different scales. One of them is obviously it depends on whether the wavelength you generated is bigger than the size of the bubble or smaller than the size of the bubble. Another relevant scale is Hubble. Okay, so if the wavelength that of the gravitational wave we're considering is bigger than the Hubble size, I call it IR. And then when the wavelength is shorter, smaller than the size of the bubble, I call it UV. And then there's some intermediate cases. It turns out this intermediate case is the most interesting. And so let me just, yeah, so this is the typical spectrum that you see. And so the shape of this spectrum is pretty easy to solve. You just solve the standard set of equations. This is for the IR, you have this KQ behavior. For the intermediate is about 1 over K. And for the UV, actually depends on the detailed numerical simulation of the bubble. Okay, so the simulation we took, it depends on the K to the some power, higher power.
What's the overall scale of this compared
Yeah,
to?
I haven't talked about that yet. Let me get to it later. I'll get to that later.
Compared to just the H over M Planck from de Sitter, this is.
Yeah, this can be bigger. It depends on the latent heat that's stored in the phase transition. Okay, let me get to it. I'll show you. Yeah, let me just another prominent feature you see that is oscillations. Okay, I wanted to give you an explanation of those oscillations. This is happen during this intermediate scale. What's happening there is that so first of all, you don't have to care too much about detail of the bubble for this because the wavelength is bigger than the size of the bubble. And roughly speaking, we're looking at an instantaneous source of gravitational wave. So everybody start at the same time and they start to oscillate. And when they move outside the horizon, the amplitude freeze. Okay, when the weird amplitude freeze to depends on how many oscillations you're allowed to make before you exit the horizon. Okay, so therefore, in the end, the signal you get a shape that's oscillating K. It is very similar to the sound horizon on the CMB. So the reason behind this oscillatory scenario. What you need is the instantaneous source and a way to freeze the oscillation. Then you get this kind of shape. Okay. Yeah. Anyways, there is this UV part I already mentioned. This particular power depends on the details of numerical simulation. This is just the case for the particular example that we took. Yeah. So this is the size. Okay, these are the size, and this is again compare with the radiation, and this is the piece that depends on the latent heat. Depends on how much latent heat you think is stored in the spectator sector, right? So as a fraction of the total, if you still want the spectator sector to be just a spectator, right? So it's a subdominant fraction. So maybe you take an example like a 10%. And there's some h over beta dependence. There's h over beta square is the standard universal dependence, and the rest of this power depends on the detailed modeling a little bit.
So you 10% to expect like 10% feature in the density spectrum at that scale.
Yeah. So there's a square, depends on that square, because it's like a Newton's law. M times M is the gravitational potential. So this is the energy of the bubble times the energy of the other bubble. That's roughly speaking the gravitational potential energy stored in the system. So it's actually that. So it's not out of the question. That's the only thing that I want. It's not the.
So what beta was the size of the scale?
Beta is the size of the bubble. Typical size of the bubble.
for like these first order phase transitions, like after inflation, like this omega gravity wave depends on like beta rates, usually to like a much smaller power.
Yeah,
right?
so as I said, it's the standard thing is square.
Squared, yeah.
Square is universal for both, right? This additional power, it depends on the detail of the, I don't know, that you're using. So this is the peak spectrum. This is the spectrum close to the peak. Okay. So this is not my work. This is just I wanted to briefly mention that we talk about first order phase transition, but even second order phase transition, you can actually you don't have domain, you don't have a bubble walls collision, but you do make topological defects. So this is one of those examples where there is a second order phase transition where C2 breaking generates a domain wall, and domain wall can source gravitational wave. I don't know too much detail about this work, but they show that it's possible to give you some observable gravitational waves.
Still during inflation.
During inflation, yeah, during inflation. Okay. All right. The next topic I want to talk about primary. Those are the
I just went back to the previous case. You can also have situations where you don't see gravitational waves directly, but the fact that you have inhomogeneities in this sector, like it can feed back into the inflationary perturbations. Is that right? Because you have like 10% of the energy density.
Yeah, you could in principle. Yeah. So let me. I wanted to talk about maybe it turns out in that case, in some cases even the secondary is more important because you also induce curvature perturbations. Let me talk about secondary. So this is the one I talk about is primary. Is the T mu during inflation literally source gravitational wave. But there's also this secondary wave. So the picture is that something happened during inflation that induced scalar perturbation. That's not the big news. Right? Inflation itself induced scalar perturbation, but maybe something else can do something even stronger than the inflation. And those scalar perturbation will evolve outside the horizon, and when they re-enter the horizon, they start to oscillate. Okay, if they enter during the era where you have pressure, you have radiation, and they will oscillate, and they will generate gravitation. This is not the gravitational wave literally generated here. It's generated here, but the source is generated during inflation. So this is called the secondary gravitational wave. Okay. So okay. So now the question is, okay, what kind of scalar perturbation do we expect beyond just the inflation itself? Okay, and so here we look at the very simple model. Okay, just the simplest model. Let me add another spectator sector. It's a scalar. Okay, simple real scalar, and the only thing I want is the mass is less than h, but it's non-zero. Okay, so what this does is that this field will not be stuck somewhere. Okay, it will not not like an axiom. It will not stuck somewhere. It will oscillate. Okay, and then oscillate will generate a spectrum of fluctuations. Will generate scalar perturbations and so on. Okay, there's a whole formalism deal with this, and it's called a stochastic this kind of stochastic perturbations, and using Fokker-Planck equation and so on. Okay, and in the end, it will spit out a power spectrum. Looks something like this. This is the function of k to some power. Okay, so let me just give you a little bit more intuition about what this power is. Okay, what this thing is in the simplest case.
I'm sorry, so this is with a mass that's less than h, but not much less than h?
It's like a 0.2 h, 0.1 h, but it's not like it's not let me just say it's not small. There's a numerical statement you can make. Okay, it literally depends on the potential that we're talking about for this scalar, right? It's just the only requirement is that it's not like axiom stuck out somewhere.
So it's not much less than h.
Yeah, it depends on this detail of this potential.
And its initial condition is that it's at 0 in the minimum?
The question is, the point exactly is that if you satisfy those conditions, it doesn't matter what the initial condition is. It will always go down to 0, then.
Right, but the phase you're looking, the interesting thing here is after it equilibrates.
Yeah, after equilibrated. Presumably this happens like during the 1,000 equals before the end of inflation, and but I'm only looking at much later. Okay, so let me just give you a little bit intuition about the power here. So the sort of the intuition we should have is that this field, when they are inside, when the mode is inside the horizon, they are still fluctuating, just like the usual inclination. So the amplitude is roughly h when they exit the horizon. When they exit the horizon, the classical equation motion starts to matter at the super horizon scales. Okay, the fluctuations start to be less important if you're thinking about the super horizon scales, and that will tends to damp the fluctuation because the field wants to go back to 0, okay, on super horizon scales, and this will tell you that the modes that exit earlier has more time to damp than the modes that exit later. This tells me that this spectrum is blue tilted. I expect more fluctuation, more power for the fluctuation on the modes that exit the horizon later. Okay, so this is basically the power. In this very simple model, the power is just depends on the mass square over h. Okay. And of course, if you do for a more general model, you actually solve, you can numerically solve the focal plot equation, and you get some more general power. But the basic feature is that it is blue tilted. Okay. The blue tilted is enough, is important because we know that this curvature perturbation at the large scales are very strongly constrained. Okay, so you want something that is not as constrained at a large scale, but also doing something at a shorter scale. And this is exactly the kind of scenario we are interested in, and also it doesn't take much to achieve this. That's what I would say. It's just a simple scale. Okay, and of course, to translate that fully into gravitational wave, you need to tell a story about how this field evolves, and when after the end of the inflation, this field will either immediately become matter-like if the mass is bigger than h already, or take a little longer, but eventually it will also become matter-like. Once it becomes matter-like, it dilutes like 1 over a cube, and its contribution to energy density will become more important. So the fluctuation in this field will have a bigger and a bigger imprint on the curvature perturbation later on. Okay. And obviously, at some point, we assume this field decays. So putting these things into equations, and you see that it depends on the fraction of the energy density of this field as a total in the total energy density, and this field can play a quite important role in inducing the curvature perturbation. Let me show you the figure. Sorry, yeah, so anyways, let me just say one more time that this is the picture. I have modes exiting horizon, and they are blue tilted, and after that, after the inflation, and this scalar field becomes more important and start to leave an imprint on the curvature perturbation. And when those curvature perturbations re-enter the horizon, it starts to induce gravitational waves. This is the picture that this set up.
Just a confusion. Normally, I think of scalar perturbations as being frozen usually once they exit the horizon. So
the individual species, individual ones are frozen, but the total can fall.
Yeah, that kind of confuses me.
Okay.
I don't know.
Yeah, it's like anyways, yeah, but it's true.
Okay, yeah, I believe it.
Wait, sorry, I'm so confused about that too. What do you mean the total can evolve?
I think it's, if you have multiple components, it depends on the fraction of energy density. It's precisely like, for example, like in the Gravitational scenario, right? So at the beginning, you may be still dominated by the curvature perturbation induced by the original input, but then later on you are going to start dominated by the curvature perturbation induced by the curvature. So that is one example. That is different.
You have an equation, right, for how they damp? Is there a simple way to understand that? Yeah.
I don't have an equation on the slide, but this is the equation. Yeah, this is the final equation. Right? So this is the
Doesn't the scalar field becomes so oscillating?
But if it's outside the horizon, it should be frozen, no? It shouldn't be rolling down its potential.
No, but wavelengths, its mass becomes equal to the horizon, right? It's like an axiom.
Right.
Then it starts oscillating at all scales, right?
yeah. So
I see. Okay.
sorry.
Yeah, I'm
Okay.
satisfied.
All right. Okay, so these are the figures, and this is the curvature perturbation that is induces, and then you see that it has a for the wavelengths for the modes that the bigger than the decay time. So sorry, this frequency is determined by the time. The mode always this frequency re-enters the horizon at the time of the curvature of signal k. And the modes before that, the longer wavelength mode, they just become more and more important. Okay, and as time goes, because they become matter-like, and they dilute slower than radiation. But for the modes that enters, we already entered the horizon before the curvature decays, it starts to dissipate. Okay, it starts to oscillate already, it starts to dissipate. Okay, so and that's why it's become less important. How sensitive is this to M over H? How sensitive is this to M over H? So did we? Do I have a? I don't have. I don't figure here. It's the slope. For example, this slope depends a bit on the M over H. But we're not talking about the huge M over H. Right? So we are not talking about the M over H is too small. Then you probably are not really looking at you're looking at a very flat spectrum.
Yeah, well, also M over H will change by order 1 of replacement.
Yeah. But yeah. So depends on that too. Yeah. So it depends on exactly how much M over H that changes. But this is we're talking about the later in the inflation. Okay, it's not as clear that H how much H changes. But I think during the CMB mode period there is a fixed prediction. So more or less. So yeah, so I think the detailed shape depends on all those details of your model, but we are not specifying that in much detail. And the only thing I think is robust here is it is blue tilted, right? Of course, how much is tilted depends on. Anyway, so this is the gravitational wave. Signal really follows the same shape, and it's possible to see it in the future. How much time I still have?
20 minutes.
Oh, I have a lot of time. Speak too fast. All right. I wanted to just briefly mention there's a second example is that I think someone already asked a similar question. During inflation, even you have a first order phase transition, you will generate both a perturbation in the inflaton field, additional perturbation in the inflaton field, although there's much less direct constraint because we're talking about the scales much smaller than the CMB scale. And but you also will generate induce a curvature perturbation just because the phase transition. So in particular, this induced curvature perturbation could actually be quite interesting. In particular, because it's inversely proportional to the rolling. It's just a standard formula for this curvature perturbation that's inversely proportional to the speed of the input. So this could actually be interesting. And the secondary gravitational wave signal could also be quite important. But yeah, I'm not going over too much details, and just see that it's still that the induced curvature perturbation can still be inverse proportional to the slow roll form. And they will fit some signal. And so I just wanted to mention, since I'm talking about first order phase transition, I'm talking about in the regime. I talked about in the regime where the phase transition really finishes, percolates, and so on. And there is another, in principle, there's another limit, interesting limit you can consider. That's the limit where, so this group of people studied, which phase transition actually doesn't quite finish. Okay, you just make they'll make some bubbles, but they never fill the space. They don't glide and so on. But these bubbles will because inflation, this bubble will go outside horizon and they will re-enter. Okay, but when they re-enter, these are also big curvature perturbations. They're big inhomogeneities when they re-enter, and this will induce secondary gravitational waves as well. Okay, they also fit some signal. So I just wanted to mention there's this other interesting limit as well. Okay. All right. This is I wanted to mention that this is the last topic I wanted to mention. That's also I think it's quite interesting. Give us a lot of information. Is that some of the signal shapes actually also depends on post-inflationary evolution of the universe. So not just to be telling you, in principle, these signals. Not just going to tell you something about the inflation, but it can also tell you something about the evolution later. Again, give you some examples. Yeah, so let's come back to this signal, and that I talked about earlier. And but the full signal actually depends on how after the full shape actually depends on how after this signal was generated, how the gravitational wave signal propagates to us. Okay, and this signal, I draw this signal by assuming a simple cosmology with de Sitter going to radiation domination and so on, like instantaneous regime. But if you change that, the shape can change quite a bit. Yeah. Anyway, so for example, like you can imagine that the inflation is not really quasi de Sitter; it's some power law. Okay, that's one of the cases you can try to test, and also post-inflationary, you can imagine many periods with different equation of states that will affect the evolution. Yeah, so it's lots of things here. I don't want to go through every one of these, but just to tell you that the slope of this the spectrum here really depends on the propagation. The slope here is really telling you something about the background, the evolution of the background spacetime. And yeah, so this is one of those examples. If you can compare a de Sitter to radiation domination, I think, which is the purple thing here, which you couldn't see it very well, but it's like this, with a scenario where you actually have a small period of matter domination. Okay, so this is also quite standard if you imagine the inflaton decay a little slowly. Okay, so then it will just give you a matter domination, early matter domination first, then going into a radiation domination. You see that the shape of these spectra are actually quite different. Okay, so in principle, okay, in one dream world is that you see these signals with oscillations, and then you are going to say, okay, I understand where this oscillation come from, and because this is the source, instantaneous source of gravitational wave during inflation. And then once you say that, and then all these shapes can tell you a lot about the later evolution. Everything. That's where everything knows everything. Okay, and another example is the secondary gravitational wave that I was talking about, because as I said, the secondary gravitational wave is generated when those curvature perturbation re-enter the horizon. And obviously, this is sensitive to what this is, when what is the equation of state, or what is the evolution of the universe around this point. The gravitational wave is sensitive to what that is. So if you a lot of the plot I showed you assumes that we re-enters in radiation domination. Okay, that's the simplest case. You can even have a quite good analytical control to calculate those signals. And but if you again assume there is some maybe there's some matter radiation transition during this period, then what's that going to happen? Okay, so this is I think I want to emphasize this is not at all far-fetched. Okay, because at least for example for the scenario I was considering, you have a spectator field that has to decay, right? So there is a even during that process there's a matter radiation transition. Okay, so it's very natural that you should be contemplating there's something happening during the reentry, that there is a matter to radiation transition. Okay. So again, so this is not my work, but there are some work on that. Okay, so this is the secondary. This plot is the size of the gravitational potential. Okay, which is the source of gravitational wave. You can use this as a proxy of the size of the gravitational wave, very roughly. And now it depends on the mode, the frequency. You're thinking whether they are entering in the matter domination or whether they are entering in radiation domination. So for the higher frequency mode, I think this is imagining that you're entering in the matter domination period, then when you get closer to matter radiation equality, and those modes is already there, and they start to decay a little bit, then they start to oscillate. Okay, where in comparison with the mode that they enter really around the equality, this is more like a radiation. They just immediately start to oscillate. Okay, so it really depends on. So you can imagine the amplitude really now have some dependence, strong dependence on the frequency of the so. And sorry, this is another sort of more ideal but slightly contrived case where you have a very sudden transition. So the other one they are calling it a gradual transition. Okay, but this is a very sudden transition, and is that the transition from matter to radiation happens suddenly. Okay, it just the mode doesn't really have enough time to decay. Looks like. So and you see that the spectrum that it produces. So this is the first case where the spectrum looks like this, and the sudden transition case, the spectrum looks like this. They can be quite different. The size also can be quite different. And this is another. So I was talking about the matter to radiation transition, but there's another example is you can imagine that in some cases you can have a transition between a matter domination case to a kination domination case. Particularly in this case, there's some rotating axis that it was matter dominating at the beginning, then suddenly becomes dominated by the kinetic energy of that rotating field. That can give you a big enhancement on the gravitational waves. Potentially fits on signal. Okay, sorry. This is all the topics I wanted to talk about. I think I wanted to emphasize that the basic point here is that gravitational wave give you a very good tool to see the part of the evolution of the universe that's otherwise invisible to us because of thermal equilibrium. And this is obviously a very long-term prospect. Okay, everything in order to see the gravitational wave signal, measure any spectral features and so on. This is I don't know how many decades down the road. And, but I think it's also potentially very exciting because you do learn a lot from it. And, I think a lot of work is done in the post-inflationary scenario case, and I think I wanted to emphasize that as I want to show with these examples is that inflationary stage is actually a very good period to generate gravitational wave signal as well, and both the primary and the secondary gravitational waves can be interesting when it's generated during inflation. Yeah, and study them can be very informative. Thank you.
Question for LianTao. But here you have in mind like laser frequencies mostly.
So which part?
Well,
Yeah. So it depends. I guess it depends on when did it happen.
well, what I really want to ask is what about foregrounds from black holes, emerging black holes? How these signals will be really?
Yeah, I don't have a great insight into how to distinguish a stochastic gravitational wave of those from black holes. Hopefully they can. And for nanograph, I think people are talking about trying to see some in the future. They may be able to try to see some anisotropies from the gravitational waves signal, but maybe that's a sign of it's coming from supermassive black hole binaries. And even that, I think, is a little bit iffy because primordial gravitational wave can also have limitations. At least if you see something anisotropy, I think it's a strong indication it's supermassive black holes.
I guess along the same lines, I'm not sure I totally understood the answer to my first question, which was how the amplitude for these gravitational waves compares to just H over M Planck.
I think the answer is it can be bigger because there is H. Right here depends on the latent heat.
Yes.
That's stored in the spectator sector. So it depends on the energy density. So
Yeah.
in principle, it can be bigger.
Yeah, I don't doubt that it can be bigger, but I guess, I mean, the one thing we know about inflation, at least in the part that we can observe easily, is that it's really very close to the center. You see tiny perturbations and scalar perturbations. We don't see any evidence for tensor fluctuations.
But that's just a handful of equal.
True. Yeah, no things can
So
change.
we also know that it's difficult to write a good effective field theory for the 60 equal.
Yeah.
So it's not hard to imagine something dramatic may happen.
Like, lots of different dramatic things could happen. So what makes this particular dramatic thing more interesting than?
Well, I'm not saying this is particularly much more interesting than anything else, but I'm just saying more dramatic things. A lot of dramatic things happen. This is one of those examples. But you do need something dramatic to happen to source some gravitational wave. Okay? So this may not be the only way to do this. Right? There could be other things. Producing topological defect can be a way to generate a very enhanced period of particle production. Can be a way to source gravitational waves as well. Okay, but this is just one of the examples. And this
Sorry, related to what Matt is asking. So you're saying it's not easy to produce effective theory for 60. You're referring to the flatness.
I'm referring to the super Planckian.
Super Planckian field.
Yeah, but this is
in what sense that problem may suggest that there could be.
I'm just saying that
I think he's just saying we don't know what's going on.
No, that I understand.
Let's measure what we can.
I just no, that I understand.
All I wanted to say is that even if you.
We'll say something more.
No, I'm not saying anything more. I'm just saying that the naive expectation is that even if you manage to write something that is okay with EFT, and still when the field traverses a long time, maybe it's okay for the period of the CMB, but later it could have induced big changes because some higher dimensional operators can become more important.
I mean, I'll even help you out a little bit. I think
since these models don't really work, it sort of argues that maybe you have some extra field. And actually, it's one of the things we're thinking about. Is that you have extra field to value and just I mean, in other words, like what we showed in our previous paper, for example, was that, I mean, this is known that if you have a curvaton, you can save some models that don't work. So you have an extra scalar. So there's an argument that you should, that if you want some of these simple quote unquote models to work, that you probably do want an additional scalar. And if you do, then you have an argument. I mean, because the model you were talking about is kind of pulled out, right?
Which model?
This, like the large field, the naive large field.
At least I think as an effective field theory during for the modes for the CMB and the large scale structure mode, I think it might still okay, but I doubt it will work for the whole 60 epoch.
Yeah, I mean, we've measured enough stuff so that we.
But we don't have enough information at the smaller scales.
You anyway small field models. By a small field model.
A small field model probably works too. Small field is just you have to. I mean, it works. I'm not saying anything deep. I think it works. I think we all know that you have to do some little bit more. Like then you have to make eta to be much bigger than epsilon. So, yeah. Otherwise, it works. I'm not saying anything.
That would make it harder to get an observable gravitational wave signal.
That will make it harder. So if the field doesn't, at least this mechanism will not work. It doesn't really. I don't have any reason that it will be any different.
Well, in general, it's just much harder because the energy density is a lot lower, and so all the sources for gravitational waves are suppressed by something like that.
Well, you can still have the transmission because the transmission is just done by scanning.
Yeah, but there's an overall.
I think what he wants to say is that if the field doesn't travel a very big distance, then there's maybe less motivation to expect that there's something dramatic, which I agree with.
But here, Planck scale, like what one usually means by big distance is Planck scale, but in your scenario, Planck scale doesn't play a role because it's really it's a question about that sector, right?
You need some luck to do that.
Right. So it doesn't. It can still be big compared to scale there. No, I'm just saying that whether you trigger transition or not in some hidden sector, it depends on dynamics on that sector, not on the whether you travel a lot.
Yeah, the thing that it
in
makes
Planck
it easier
scale.
to have the large field value makes it easier to get an effect on that guy without having a large back reaction on the other.
Yeah.
So that's what you gain.
That's all.
Perfect. Can I ask a question? So, so you mentioned for the instantaneous and the non-instantaneous repeating, there's the signal is a little bit different. So I'm just wondering, do we have some benchmark model for the instantaneous repeating, or what about or we just
instantaneous repeating probably requires some strong coupling.
Yeah, so just turn up the coupling and make the implant decay.
Something like that. Yeah, it has to be something like that. It's a strictly speaking, really instantaneous repeating is impossible. It's contrived. You always have a little bit, but the question is whether it's instantaneous enough to be a good model.
And also, I'm wondering maybe if we have the different implant decay channels, then we can have
decay of what?
The implant decay, the reheating.
That helps. That goes into the reheating story.
Yeah.
So the things I'm talking about here is not really sensitive to the detailed reheating. The only thing that's sensitive is that whether the shape is sensitive to whether you have a early matter domination here or not. If it's not having instantaneous reheating, you have a little bit of early matter domination. It does enter affect the shape of the gravitational.
Yes. Thank you.
For the nanograph signal, you had a plot, I think, with the various striated bubbles, and you had like some gravitational wave signal through there. What was that signal? Was the slope just like a k cube causality limited slope? What was that?
It's let me see. It's basically It's basically this part.
Okay, that was from the first order phase transition.
Yeah, that was from the first order phase transition. Then there's another place. I was trying to avoid really talking about nanograph. But yeah, so this is from this. This is the
Right.
transition that they rely on this transition to enhance the gravitational wave signal. It's this I think this is the second southern transition scenario. You have to tune a little bit to make sure this transition is sudden, then the gravitational potential doesn't decay that much before it.
So it seemed like in most of your examples, you had a change in the scalar perturbations as well, right? Or at least, or maybe only in the second part, the secondary one. So that also means you change small scale structures, right? So tiny.
Very small scales, right? It could be, yes. And the question is how sensitive you are with those things. I think okay. First of all, it does get a lot of these secondary these curvature perturbations. There is a ceiling, which is primordial black hole, right? So that if they are being too big,
right,
you start to producing primordial black hole. That certainly enters.
But there's a lot of space in between.
Yeah, there are lots of space, and there are other things like the distortion and so on. Maybe sensitive to some of these. But otherwise, I think there's a lot of room.
But is it true in reverse too, that if you say there's enhanced scalar perturbations on small scales, do you then automatically produce gravitational waves as well?
I think so. Because they're just part of the they're part of the R, if you want. That also sources gravitational wave. They will also once they become interhorizon, they start also. It's pretty robust. That part is really robust. It's a bit complicated to calculate, but otherwise it's
Any last questions? If not, thank you, LianTao again.
See you soon.
Yeah.